So as we have previously explained that there are three parts of our project, and thus there are three part of the code. First one is to calibrate the camera of our PC, and for that we have written two parts of the code. One is to get the images for the chessboard, and the second one is for the calibration. We are not going to show the get images function, as it is just a simple function to get images. We are going to do the thing for the calibration part. So this is the conventional procedure to calibrate the camera. We have taken around 8 to 9 pictures for calibrating it with a chessboard image in our hand, and the chess image that we have taken is of 9,7 corners. Thus we have written 8,6 in the chessboard size. We have taken a frame size, and then we have initialized arrays. Then we have a for loop, as we have more than one images that we are going to use. We are going to use 8 to 9 images, thus there is a for loop for that, as it is going to repeat process for each and every image. As we can show that most of the procedure is conventional process, thus there are already inbuilt function like draw chessboard corners that can give us the corners for the chess board. uh, Also we are going to print the calibrated camera and the camera matrix is going to be used for the pose estimation part of our project. And then there are rotation vector and translation vectors also that we are going to print. Right now I'm going to run the code so that we can talk about the results. So these are the images that we have taken, and it is clearly shown that the corners has been detected very well, and thus the error is very low. And as we can see in the result part that these are the translation and rotational vector that we got, and the camera matrix that we can use in the pose estimation part of the code that we are going to explain later, later part of the video. And there is a distortion parameter, although we are not going to use the distortion parameter, still we are printing those things. And now we are going to move for the next part of the code, that is object tracking using homography, and that my teammate Muskan is going to explain.
First, we have used the query image and we have resized that image by using the scale factor. And here is we initialize the R web camera by using this video capture. Here is putting the 0 for using the webcam. And we have computed the key points and descriptor for the query images, and then we have compute the key points and descriptor for the frame, because in the frame we want to track the object, or in the object and query image we want to match the key points. For that we have used the algorithm by using flan, which use for the matching the two key points. And then we have used the good point. We have matched the good points over the images, and then we have draw the homography over the object that we are willing to track. Now here is the code. I want to run this code and show you the output. Here you can see easily the key points can match to the tracked image, and the minimum outliers you can see, and mostly the inliers. And in the right side image you can see the homography that is completely matched on the tracking object. Thank you. Now next part will explain by the Nishan.
Hello. So in this code, we will pose estimate of the camera. So starting with the main function, Here is the video which we use to detect the pose estimation of the camera. So the first function is used to get track. So now we will go to the main function, the get track, how we track the frame by frame of the video. So you use a CV2 video capture, which the argument of this function is video path. We will pass the path of the video which we will use to find the pose estimation of camera. So cap will contain the information of the frame, and here we made the Hoff search space, which is used to find the maximum number of the edges intersection. And in this while loop, we done the few operation of the basic operation of computer vision like Gaussian blur, canny edge detector on the frame by frame of this video. As you can see in this, we use the Hoff search space and find the maximum number of the frequency, and we choose the best top lines as this best line which have the best number of occurrences in the Hoff search spaces. Now the finding the corner point. Here we use a basic algorithm just like intersecting of the two lines, and the intersecting point is the corner point, and we append the corner point in the we made the list of corners and append the corner into that list. Now in the we display the plot. Here in this plot we display the lines and the corner of the images. And here this loop is to display the video of the edges. And after all this done for the frame by frame of the video, then we go to the next function, get h. This function is used to get the homography matrix. The basic principle is like this: we use the SVD, singular value decomposition, and the decomposition will give the result, the translation matrix and the rotation matrix. And we append this translation matrix and rotation matrix for each and every point into the R bank and T bank. This will be used here. And after this, we will plot the result with respect to frame. And this is the complete explanation of the result. I will show you the result. As the code is running time is very high, so I cannot running it, and this is the final result we obtain. As you can see, the green line is getting down. This means the camera is approaching toward the object. I will also show you the video which I am taking for getting the result. As you can see, the camera is approaching toward the object. That's why the z-axis is decreasing linearly. Thank you.